Good evening, everyone. Uh, Welcome to the sixth session for the course uh, Reinforced Soil Structures. In this week, we have discussed about the slope stability analysis of reinforced soil slopes. Earlier, we had discussed about reinforced soil walls. The analysis method of analysis is approximately similar, though with the only difference that you have additional slope stability analysis, which is missing in reinforced soil walls. So we discussed a few cases, and in today's session, I wanted to uh, showcase you some practical problems, but unfortunately, it's raining very heavily here, and I'm not able to connect to the VPN of my institute, so I don't have the license for the software, but nevertheless, we'll discuss the theoretical part, and we have some results in the PDF form. So we'll try to make sense out of it. And if you have any questions, you can ask, and we can discuss the particulars in the next week. So we'll start by discussing a very simple case of a reinforced soil wall with geosynthetics. This problem was also discussed in the first session, but since you had not studied the theory by then, uh, it's good to revisit this problem again since we have studied the theory. So reinforced earth walls or MSE walls. RE walls term is generally not used. It's a proprietary term. You either use mechanically stabilized earth walls or reinforced earth walls. So it's written that you have different types of reinforcements, and so uh, it's written about that there are two methods available for defining the geosynthetic pull out resistance. So if you have a reinforcement in which the uh, stress transfer mechanism is passive resistance, that means bearing, where the bearing is dominant, then it is not dependent on the overburden stress. Whereas if the pull-out resistance is dependent on the friction of the reinforcement, then it is dependent on the overburden. So these are the two different approaches which can be used. Generally, the friction one is used, but if you have the bearing one, then the pull-out resistance is provided as force per unit length. It is a fixed value, force per unit length per unit width in the out of plane direction. So this is a constant value. It is independent of the overburden stress. Whereas if you see frictional resistance, this is the usual approach that we use, where it is the Mohr Coulomb value, and we multiply the overburden stress, effective stress, by tan of delta. And here SAF is the surface area factor, which is the mobilized pull-out resistance. The total area on the top and bottom may not be able to provide enough, may not be completely mobilized. So that is why SAF value is used. And then you have resistance reduction factor, uh, which is due to various issues of uncertainty. And then you can see here that the value here is given Pull-out resistance is given as force per unit area. That means bearing is dominant. Its friction is not dominant. Whereas if you click on the calculate pull-out resistance, then it is dependent on the overburden and friction is dominant. So sometimes there might be a case that both take into both values are dominant, such as the case in geogrids, where bearing is also dominant and the friction is also dominant. So you find out the equivalent interface shear angle, which accounts for both bearing and friction, and then use it in this. The second factor is the tensile capacity. You already know that there are two governing mechanisms for a design of reinforcement. One is the tensile capacity and one is the pull-out resistance. Both values are given. And here again, the reduction factor has been used. There is an option of factor of safety dependent, which means that this reduction factor is actually dependent, is used if factor of safety, if it is independent of factor of safety. Otherwise, if it is dependent of factor of safety, this value will be equal to the factor of safety that you have calculated. So yeah. Now, suppose this is our geometry, a very simple geometry. You have four layers, geosynthetic layers. The value is given. It's a friction angle of 30 degrees and which appears to be a strong soil. So most likely it will be a plane wedge failure rather than a slope failure. Then Spencer limit equilibrium method have been used. Either you generally use Spencer limit equilibrium method or Morgenstern price method. These are the two methods. Otherwise, you can also use the method of slices, and pore waters are not defined. And in this example, three cases are used. The first case is when the reinforcement is not dependent of the factor of safety. That means individual reduction factors are used and the pull-out resistance is constant. It is the main action is bearing. Second analysis is that the reinforcement depends on the factor of safety. And the third case is that the pull-out resistance is actually dependent on the friction value rather than the bearing value. And that's why we have to give an interface shear angle, which is equal to phi only. Delta is equal to phi. So these are the different properties which has been provided. So you can see the length is 9 meters and pull-out resistance is actually constant. But in the third case, it is calculated based on the overburden values. And these are the resistance reduction factor. And these are the tensile capacity. So for the first case, your resistance, the pull-out resistance will be 70 kilonewton divided by 1.5. So that will be 50 kilonewtons and maximum tensile case will also be divided by the reduction factor, which will come out to be 120 kilonewtons. So this is 50 kilonewton is per meter length. So if you calculate for 2.4 meters, then the value will come out to be 20 kilonewtons. So that tells us that if the embedment length is greater than 2.4 meters, then the pull-out resistance will not govern and tensile resistance will govern. Because if it is greater than 2.4 meters, the value will exceed, say, up to 150 kilonewtons, but the maximum tensile capacity is only 120 kilonewtons. So, but this tensile capacity will govern rather than this value. So it is advisable that we design our reinforcement such that we at least get 2.4 meters Otherwise, if this value is less, then the the contribution of the reinforcement would actually decrease below 120 kilonewtons. So we will first find out the critical slip surface for the base case for the first case. And we find out this is the result. It is almost similar to a planar wedge analysis. If, you can also calculate the factor of safety for this case. And we can after discussing this, you can actually try to kind of calculate the factor of safety. This will come out to be around 1.4 only. So here you can see the red portion marked on individual reinforcement layers corresponds to the length 2.4 meters, which is outside the failure zone. So this 2.4 meters correspond to a pull out capacity of 120 kilonewtons. So since more values, more embedment length is available than 2.4 meters, then the tensile capacity will govern the strength of the reinforcement layer. So now let's look at the second case. Here we got the factor of safety of 1.4. So remember the reduction factors that we had provided in the first case was 1.5. Now, since the factor of safety is almost near to 1.5, we don't see a lot of difference between the first case and the second case because the value is are approximately same only. Otherwise, if you would have use different reduction factors, or if the uh, factor of safety was different, then there would be a difference in the analysis. So this is the second case, and now let's look at the third case. Now here in the third case, you can see that the reinforcement capacity of the uh, topmost layer is not sufficient because the overburden is less. Since it is dependent on friction, the overburden is less, and that is why you require more embedment length than the other layers. You can see the value for the last case is the smallest, and if you go upwards, the length increases. So that's why for the uppermost case, the length of the reinforcement is usually the highest, as we have seen. And as you go down, the length of the reinforcement can be reduced. However, it is opposite to the spacing because you have to decrease the spacing as you go down because the amount of force the the reinforcement layer encounters increases with depth. So one is the spacing and one is the length. So here you can see that this value is not sufficient in the first two cases. That means that it will not be able to provide a resistance of 120 kilonewtons, but rather whatever is the pull-out resistance corresponding to this length, embedment length. So that is why, since this value is not being used, the factor of safety has reduced significantly from 1.5 to almost 1.2. So this is the case. Now, I would like you to give it a try. This question, this part. This has been already uploaded. And there is another problem which has been discussed. That is for a 37-meter high MSC wall. It's a practical case. And some images are also given. So also go through it at about, this is a long document, so it will take some time. So at about 8:10 p.m. we'll discuss this part also. But So the task for you is that first of all, you have to calculate what is the factor of safety using the linear wedge method. And then you also have to go through this and we'll discuss this part uh, after at around 8:20. Thank you. For those who have just joined, uh, we have discussed a problem case for a practical problem case reinforcement with geosynthetics. We wanted to give you a tutorial on a practical problem, but unfortunately, the Institute VPN is not working and I don't have the license currently. So we can discuss it in the next class. Uh, we have discussed that there are two types of reinforcement stress transfer mechanism. One is the bearing and other is the friction one. So in whenever there is bearing, you have the pull out resistance as fixed and it is equal to force per unit length of geosynthetics. Whereas if it is friction, it is not fixed. It is actually dependent on the overburden pressure. So as you go deeper, the pull out resistance per unit length would actually increase. So then we discussed a case, multiple cases. One first case is when the pull out resistance was constant. This represents the bearing case. And then you have tensile capacity. And then we did our numerical analysis for the given case. And the three different cases. Then we calculated the factor of safety and the bed length was constant because uh, the major governing factor was the the bearing. And then we have another case and third case where friction was dominant. So you can see that the embedment length required is actually decreasing. So you have to solve for this case and find out what is the factor of safety. And then we will solve McAfee. So let us discuss this second problem. Uh, it is a 40-meter wall which was constructed in Albania, and you can see this is the wall. So these are the gabions, rock-filled gabions, and this is a twisted wire mesh which is installed with these gabions. This is only to support this gabions. It is called Terra Mesh, and it is a proprietary system for of the company McAfee. And so this, please note that this wire mesh does not contribute to the to the reinforcement of the soil because this length is very small. Here you can see the whole cross section. The length of the wire mesh is only this, whereas the length of the reinforcement is very, very high. And you can see there is some backfill soil, and this is the original slope, which is known as the foundation soil. So if you do a regular analysis without the reinforcement, uh, since the foundation soil has a phi of 46 degree, it will not fail. So you will have a linear wedge, and that will be the critical failure surface. So this is the analysis without uh, considering the reinforcements. Here, this orange one is the backfill soil. Then you have structural soil, and then you have the gabion block. Each have its different cohesion value and phi value. So you can see for the structural soil, the phi is the least. So most likely that the critical failure surface will pass through this. And there is some top load due to the traffic is also applied. And there is no horizontal seismic load applied in this case. So we have multiple cases. First case is when there is no reinforcement. Second, reinforcement without seismic, reinforcement with seismic. Then we have global stability and we have internal stability for the two cases. So here, uh, this active wedge failure is not considered for the individual benches, but for the whole slope, the analysis is conducted. As you can see, this failure surface, this line represents the start of the failure slip surface, and this line represents the end of the slip surface. So all the slip surface are drawn from this point to this point. So it is this will not include the active wedge for this. And so you can see that this is how you design the different reinforcement sets. So this is the most topmost one where the length is 10 meters and the spacing is about 1 meter. And you calculate what is the reduction factor. And these are some of the properties. This is the theory. Now let's see at the results. So here, if you see, as told, that the critical failure surface is depicted by this white line. Here it is a linear wedge and the factor of safety is 0.46. So it is unsafe and we require the reinforcement. So the length of the amount of reinforcement can be calculated by the formula discussed in the course. So using that, you can get an idea what should be the number of reinforcement, and then what will the spacing is decided based on the what are the individual tension forces which are applied at this. So this is when the reinforcement is applied. So here you can see that the failure surface shifts towards the left and almost goes beyond the reinforcement layers. And so this is the critical. This is all, I think, going through the foundation soil because the reinforcement has increased the strength of the structural soil. That's why the slip surface is not passing. So the factor of safety is now increased to 1.5, but this is without seismic load. If you apply seismic load, the factor of safety decreases to 1.45. And this is Morgenstern price method. So you have factor of safety for load equilibrium and you have a factor of safety for moment equilibrium, and both these values when they meet for different lambda, that is the actual factor of safety. So here they meet and that's the actual factor of safety. And this is the global stability analysis. So here you can see that the slip surfaces are outside the reinforcement zone. So here the factor of global factor of safety is 1.53. And so this is it. If you have any questions, you can ask. Um, Otherwise, I'll see you next week at the same time. Thank you very much, and I wish you a very good night.